Hello everybody and welcome to Scalar's YouTube channel. This is Mahima Hans and I'm a software engineer and a mentor. And this is part 3 of our sorting algorithm series. In the previous videos, we discussed bubble sort, selection sort, insertion sort and merge sort. And today we're going to be covering another important algorithm, which is the quick sort algorithm. So before we get on with the video, make sure to check out Scalar's free masterclasses by industry-leading experts only on Scalar's events page. The link is in the description. So let's get started. So talking about quick sort, this algorithm is definitely more efficient than all the algorithms that we've already covered. But it's important to know and understand all the algorithms, since different algorithms can have different applications in different problems. We'll be covering in-depth explanation of the quick sort algorithm today. We'll be covering the pseudocode and we'll write and run our C++ code. And we'll be also discussing the time and space complexity. So let's try to understand what the quick sort algorithm is and how exactly it works. So quick sort is a sorting algorithm based on the technique of divide and conquer. We've already studied merge sort algorithm, which was also based on divide and conquer. And quick sort is another such algorithm. And how it works is, it picks an element as a pivot and partitions the given array around the picked pivot. So what it does is it will pick up a pivot and it will place the pivot in its correct position first and partition the remaining array around the pivot. So the target of the partitions is to place the pivot at its correct place and put all smaller elements to the left of the pivot and all greater elements to the right of the pivot. And after this is done, after the pivot is placed in the correct position, we use recursion and we sort the left and right side of the pivot as well. So the partitions that we created are also sorted by the same technique and the recursion goes on. So this finally sorts the array, and to understand it better, let's consider an example. So let's say we have an array which is, let's say it has 5 elements. It's 1, then 9, 3, 8 and 4. So we have these 5 elements and it's an unsorted array. Now we want to sort this in increasing order. So we want the desired state to be 1, 3, 4, 8 and 9. So first, as the quick sort algorithm says, we have to pick a pivot element and we have to place in its correct place. So pick a pivot, partition correctly. So partition correctly means left on the smaller elements on the left and larger elements on the right. And then recursion for the partitions. Recursively sort partitions. So we'll be performing these 3 steps on every array. And even if we go recursively, then we have to apply quick sort again, right? So we'll be performing these 3 steps again and again. So according to the algorithm, we'll first pick up a pivot element. And there are different ways of picking up a pivot element. The first thing we can do is we can always pick the first element as a pivot. Or we can always pick the last element of the array as a pivot. And we can also choose the middle element of the array as a pivot. Or another thing we can do is choose any random element out of the array as pivot. So for the sake of today's explanation, I'll be considering the last element of the array as the pivot element every time. So here, pivot element will be 4, as it's the last element. Now, our first step is done, pick a pivot. The second step was partition correctly. Smaller elements of the 4 to the left side and smaller elements than 4 to the left side and larger elements to the right side. And it also means place pivot at the correct place. Correctly, place pivot at the correct position. So now our task is to bring 4 to its desired position. So now this was our initial array and this is our desired array. The desired position of 4 is index 2. So we have to bring 4 at index 2. After we apply our second step, our state should be 1, 3, 4, 8, 9. It should actually be 1, 3, 4, 9, 8. I'll tell you the reason why. For the second step, we have to place the pivot correctly. We have 4 at the right position, and we have to place the smaller elements to the left and larger elements to the right. So smaller elements than 4 were 1 and 3. So they're coming to the left. Larger elements were 9 and 8. They're coming to the right. So their order won't be changed. The elements smaller will remain in same order, but they'll come to the left. The elements larger will also remain in the same order, and they'll come to the right. Desired state after the second step is this one. Now we move on to the third step, which is recursively sort these partitions. So now since 4 is at the right place, our problem reduces to 2 subproblems, which is the 2 partitions that we've got. So one is before 4, partition before 4, and which is the smaller elements, and the other is partition after 4. So now we have 2 arrays, 1, 3, 9, 8. So now we'll solve these using the same method. Let's apply these 3 steps again. I'll pick a pivot. So picking up a pivot is picking up the last element. Let's pick 3. Now place the pivot correctly and bring the smaller elements to the left, larger to the right in the same order. So now 1 is smaller than 3, it's already on the left, and there's no larger element than 3. So 3 is at its correct position. Elements smaller than 3 are on the left, larger than 3 don't exist. So this is essentially sorted only, which means our step 2 is already done. So the correct position is done, smaller, larger is done. Now we have to recursively sort the partitions in this array. So when we put 3 at its right position, which was the index 1, there's no right partition because there was no element greater than 3. But we do have a left partition, element smaller than 3, which is just 1 element. So now our subproblem reduces to nothing here and the element 1 here. But this is already sorted, right? 1 element we can't sort it, it's already done. So this is fine. And the left part is sorted. So the left part, since we had to return here, so till here the left partition is completely sorted recursively. Now coming on to the right part. Here also we have to follow these 3 steps. So I have to pick a pivot, picking up the last element, which is 8. I have to partition correctly and bring 8 at its right place. So currently it was 3 and 4. So I have to bring smaller elements. So also, like when you are referring to this array or the subproblem, we don't need to care about the rest of the array. So we're only concerned with this part, which is the index 3 to 4. This is one of the problems that we're solving. 8, bringing 8 at the right place, and 9 after 8, because 9 is greater than 8. And there's no element smaller than 8, so we can't bring any element to the left of the 8. So nothing is there in, so doing the second step, we'll place 8 correctly, where smaller elements which don't exist and larger elements are on the right. Now the next step is recursively sort partitions. So to recursively sort partitions, no partition on the left, only 9 on the right. So if we try to sort 9, we don't need any work. So this is also sorted. So we return the sorted 8 and 9, 1 and 3 from here, 4 was at the right place. So a final array after doing these 3 steps becomes 1, 3, 4, 8 and 9. And this is exactly what our desired state was. So this is how quicksort essentially sorts an array. It's a recursive algorithm, works on divide and conquer. How is that? We're dividing the array into subproblems and then solving those subproblems to calculate our final result. So it works on divide and conquer, and it uses recursion to sort the elements. So now that we've understood the different steps of quicksort algorithm and how it works, let's try and figure out how to implement the solution of a quicksort algorithm. Since we discussed there were 3 steps, Pick a pivot, place it correctly, partition the array between smaller and larger elements than the pivot, and then recursively sort the left and right paths. Among these three steps, picking a pivot is easy. Since we discussed, we can just essentially pick the last element of the array as the pivot in our implementation. And recursively sorting the left and right part is also just a recursive call that we have to make. The main part that we have to work on in the code is placing the pivot correctly and partitioning the array correctly between the smaller elements than the pivot and the larger elements than the pivot. So let's see how this is done. So we'll take the array. We'll just mark our low and high elements in the array. So low means the first element of the array that we are considering, and high means the last element of the array that we are considering. To find the correct position of the pivot, so let's say in this case, our pivot is 8. Or let's take the previous array only, the one that we were considering. And here it was 1, 9, 3, 8, and 4. So here the pivot is 4. This is low, this is high. And now we have to find the correct position of the pivot and then partition it correctly. So for that, we have to iterate through all elements of the array. So since this is the pivot, we have to iterate through all the remaining elements to find those which are smaller and push them to the left side. To write this logic, what we do is we start from the leftmost element. So here we'll start from 1 and we keep track of the index for smaller or equal elements as I. So we'll have an index as I that will, so all the elements till I will be either smaller or large or equal to the pivot element. So after I, one partition will get over. So initially, since we're just starting out and we don't really know which elements are smaller than the current pivot, we'll keep I at -1 position. So currently our I is here. As we proceed, if we find a smaller element, then we increment I and we swap the current element with ARRI. Whenever we are finding a smaller or equal element as the pivot, we will just increment I, saying that we are moving I forward. So it means the elements which are smaller than I or which are smaller than pivot or which are equal to pivot have one more count increased and they are till the ith index. So we'll swap that, and if there are larger elements, we'll simply ignore them. So let's try to dry run it for this case and then we'll be able to understand it better. So we had I initially and I was placed at -1 position. Now what we do for pivot 4, we iterate through the whole array. So we start from 0th index. So we're at 1. Is 1 smaller than 4? Yes, it is. Which means I should be at 1, or at least the value 1 should come in the elements which are smaller than 4. So what we do is we increment I. So from -1, I changes to 0. The position of I changes to 0 and we swap the current element. So this is ARR of 0 with ARR of I. So since here the position 0 and is the 0 and 0 are same, so 1 sits here and I comes here. Now we move on to 9. So since 9 is not smaller than 4, we move forward. Now we come to 3. So since 3 is smaller than 4, we have to increment our I, saying that the number of elements which are smaller than pivot have increased, and so we have to incorporate those elements before I or at I, so that I acts as the smaller partition. The I acts as the last index of the smaller partition. So we'll increment I becomes 1, I comes here, and we swap the array at the position that we were at. So we were at 3, right? We were iterating from, we started iterating from 0. Initially we were here, then we were here, then we came here. So we will swap this with the position, the element at position I. So what we do is we swap 9 and 3. And let's call this pointer J. So swapping this will give 1, 3, 9, 8 and 4. And I will be here. So if you see up till now, all the elements smaller than 4 are before I. So all the elements, so that's our goal. We have to bring smaller elements than 4 before or at I. You might have a question. Wouldn't swapping mess up the sequence of elements or, make the order wrong? It wouldn't affect, because what we're doing is we're essentially bringing the smaller elements forward and we're incrementing I. And if we are swapping with any element, that will definitely be a bigger element. And that has to definitely get to the right. So if we swap the element at index I with the current element, that wouldn't mess up the order of the array, elements in the array. So moving on, after 3, we encounter 8. So 8 is not smaller than 4 and there are no more other elements left. So we stop here. So this is how it works. So we have all the elements left less than 4 before or at I, and the value of I is 1. Now what we do is we take the index I plus 1 and we swap the element at the last index, which is the pivot. So essentially, if all the elements smaller than 4 are at or before I, 4 can come right after I. So we just take this element and we swap them. So our array becomes 1, 3, 4, 8 and 9. This is what happens when we place it correctly and partition it correctly. Now the next part is sorting the left and right part. So now let's consider our left part, which is a 1, 3, and our right part, which is 8, 9. After this state, we have these left and right parts. Now again, we'll do the same thing. We picked up a pivot and we have to place it correctly. So to place it correctly, we'll start from the beginning of the array. So we'll start from here. Our I will be here, -1 again. J will be here. And as soon as we encounter an element less than pivot, we'll increment our I and we'll swap them. So I becomes 0 and we have to swap array of I and array of j. But since they are the same, there's no difference. So 1 stays here. And then the elements we have to iterate end here. So now this is correct, and since I is at position 0, the correct position for pivot would be I plus 1. So the correct position for pivot is I plus 1, which is 1. And the pivot is currently at 1. So even if we swap them, it doesn't make any difference. So this is in the correct order as well. So what we essentially did was, we brought all the elements smaller than or equal to the pivot element at or before I. And then all the elements left were greater than I. And then we put our pivot element at the I plus 1th place, because all the elements smaller had already come before I. So after I plus 1, there'll be either the larger elements or no elements at all. Let's also see the same thing in the right part of the array. So here, if we take pivot as this, 9, and if we start from here, the I will be -1 and j will be at 0. So since we encounter an element less than pivot, which is 8, what we'll do it, we'll just increment I and we'll swap array of I and array of j. And then since they're both essentially the same, it doesn't make any difference. And that's how the order remains. It remains 8 and 9 only. And now that we've sorted, we've created the right partitions, we could even divide it again into partitions and try to sort them out. But only one partition is there, which is the left one. And that too just has the one element. So it doesn't make sense to sort because it's already sorted. So that's how it works in code. To try and write the pseudo code for this, for the better understanding before proceeding to the code, let's try that. So for the pseudo code, let's consider this array again. And now we'll be writing a quicksort function. So for the first 2 steps, I'll be using a helper function to do all of this procedure. So picking up a pivot and placing it correctly on the right position and then partitioning it. So let's say we have a partition function. And what the function is doing is that it is taking the low, high. So low and high are the indexes. So this is the indexes between which the current array is being considered. So partition will take these 2. And partition will give us the index where the pivot element has to be placed. So first, this will pick up a pivot. Okay. We'll write this function later. I'm just writing the recursive calls for now. So this is our main quick sort function. And in the partition function, we'll have three things. We'll be picking up a pivot. When we'll be partitioning the array correctly. And then we'll be returning the correct position of the pivot. So once the correct position of the pivot is returned, let's say we return that the correct position of pivot is index 2. So we know that before index 2, there's one partition of elements smaller than the pivot. And after the index 2, there is the other partition of the elements greater than the pivot. So now we'll go ahead and actually sort these two partitions in a recursive manner. So what we have to essentially do is we take the partition index, then we actually make the recursive calls. So we'll be making a recursive call wherein our initial index will become the same. Let's say here our partition index came. So initial index will be the same. And the partition's endpoint will be partition index minus 1. Because partition index is the position of pivot. And the left half will be the first partition that we have to deal with, and the second partition is starting from partition index plus 1, just next to the pivot element's right position, and going till high. So this is how the array will be partitioned, and this is how the recursive calls will be made. Now once this is done, let's try and understand how we'll define the partition function. So for the partition function, we'll always consider so it'll take low and high. Let's just quickly do it. It'll take low and high. So we'll just assign the last element as the pivot element. So let's say int pivot value, let's say it's array of high, right? Now what we have to do is we have to, remember I talked about an I index which will represent all the elements. So wherever the index I is, till that position, all the elements that are present are smaller than the pivot element. We have to calculate that I index effectively. And initially, in the last example, we initialized I with minus 1. But if you take a more generic implementation, I will be initialized to low minus 1. Because when we do partitions, so when we will be dealing with this partition, I will be 1 before this index. So I always comes before. So let's say in this partition when we go, whenever we encounter any partition between the array, there'll be a low and high. And I has to be right before the low index, right before the array. So I will be always low minus 1 initially. So we'll consider I as low minus 1. Now we'll iterate through the array. So let's take a j pointer to iterate. And for j, we will start from the low. We'll go till high minus 1. Or we can go till high, it doesn't matter. High is already the pivot. And then we can do a j++. What we were checking is if the current element is smaller than the pivot. So if current element is smaller than the pivot, if the array of j is smaller than the pivot, we'll essentially increment our I, indicating that one element smaller than I has come, and we'll put that element at the I position. So we'll be swapping ARR of I and ARR of j. And once this is done, we'll be simply assigning ARR of I plus 1 as basically, since we already know that all the elements lesser than pivot are already before or at I plus 1 will be the partition index. So that's what we have to return. And we can also swap ARR high. So initially pivot was at ARR high. So if we swap ARR high with ARR of I plus 1, that's what will bring the pivot at the right position. Because the pivot's right position is identified as I plus 1. And now we can just return I plus 1 because that's the correct position of our pivot element. So now let's move on to the code of quicksort algorithm. So let's try to solve this on lead code. I'll define a function quicksort. It will take our array. It will also take the low and high indexes as I told. So let's say our low is 0 and let's quickly calculate the value of n, which is nums.size. And the high initially would be the last element of the array, last index, which is n minus 1. Now I'll define a quicksort function. Let's say void quicksort. We'll pass the vector by reference. We'll pass the low index and we'll pass the high index. So initially what we were doing in our pseudocode was finding the partition. And this partition finding was essentially setting up a pivot element first, then arranging the elements smaller than pivot towards the left. I mean, it was placing it till the ith index, and then it was putting the pivot element at its correct position and returning that position. So let's say we'll write this function later, but currently I'm just calling a partition function, and I'll be passing on the nums array, the low and the high value. After we've found the correct element, the correct position of pivot, now our task is to sort the elements to the left of pivot and elements to the right of pivot using recursion. So I'll call quicksort for elements to the left of pivot, which would be starting from low, going till pi minus 1. And calling it for the right part, so it would be starting from pi plus 1, and it will be going till high. Now we gotta have a base case for our recursion. So remember, whenever we were left with either one element or no elements at all, so if any partition was empty or there was just one element in a partition, that doesn't need sorting and we can simply return from there. So we can write the base case if low is greater than equal to high. So if low is greater than high, then essentially there's no element, and if low is equal to high, that means there's only one element, which is the low as well as the high. So in that case, we can simply return. Now moving on to the main part of the code, which is writing the partition function. So I'll quickly define the partition function here. It takes all these three parameters. I'll pass it similarly. Okay, so first we will just consider our pivot element to be the last element of the array. So our pivot element would be, let's just call it nums of I. Now we have to start I from low minus 1, as we discussed. So initially, since the array is from low to high, we are considering that since we haven't figured out which elements are smaller, which are not, we are considering that I is just outside the array, and as and when we find any element which is smaller, we'll swap the element with the I index after incrementing it. So at the end, let's say we don't find any element smaller. So what we do is we consider that I plus 1 was the correct position of the element. So let's say our array was, let's say it was 2, 4 and 1. So our pivot will be this, and our I will be placed at this position, right? Now, when we go through the array till here, we find no element which was smaller than the pivot element. So at the end, what we are deciding is that the correct position of the pivot element is I plus 1. And if I plus 1 will be this position. So this means it will still put our pivot element at the right position, which is the first position. So they'll be swapped and it will still work correctly. So now we're starting I from low minus 1. We're iterating over the rest of the array other than the pivot element. So we'll start j from low. We'll take j to less than high, and we'll increment j in every iteration. Now we'll check if the array at this position is less than pivot. In that case, we'll increment I, and then we'll swap nums I and nums j. After that, since all the elements smaller than or equal to pivot have already come before or at I, so now we can simply say that I plus 1 would be the correct position of pivot, as all the elements smaller have already come before I plus 1. So we'll just say swap ARR I plus 1, let's call it nums, and nums of high. A little typo here, nums of high is the pivot, the last element. Now since I plus 1 is the final index, is the correct place of the pivot element, that's what we'll return from this partition function. So let's try and run our code. We have a small typing error. Okay, so here we have to return the array. So we've already passed by reference. This would have changed. The partition function is also an integer type. Yeah, so it got accepted and the arrays were sorted. So that's how quicksort works. We'll try and submit this solution. So talking about the time complexity of the algorithm, just as merge sort, this also has an average time complexity of n log n. So since we're dividing into two arrays at every step, and then for sorting all the partitions, the max it can take is O of n. So average, it comes out to be log n into n. The worst time complexity for quicksort can be O of n square, because the worst case complexity can occur when the pivot at every step consistently results in highly unbalanced partitions. So when the array is already sorted and the pivot is always chosen as the smallest or the largest element, in that case n square complexity can be there. And to mitigate the worst case scenario, various techniques are used, such as choosing a better pivot. For example, we can choose a median of 3. Or you can use a randomized algorithm, or randomized quicksort algorithm is there to shuffle the elements before sorting. So now let's discuss the advantages and disadvantages of quicksort. So one of the advantages is that since it's a divide and conquer algorithm, it makes easier to solve problems. And it's really efficient on large data sets. It also has a low overhead since it only requires a small amount of memory to function. Now talking about a few disadvantages of quicksort, it has a worse time complexity of O of n square, which occurs when the pivot is chosen poorly. And it's not a good choice for small data sets. Also, quicksort algorithm is not a stable sort algorithm, meaning that if two elements have the same key, their relative order will not be preserved in the sorted output in case of quicksort. Because here we are swapping elements according to the pivot's positions without considering their original position. So this was about the quicksort algorithm. I hope you were able to understand what the algorithm is and how we implement it. So if you got value out of this video, make sure to like it. If you have any doubts or any comments, feel free to drop them in the comment section below and we'll be happy to answer. Subscribe to Scalar's YouTube channel for more such informative content. Till then, happy coding and see you.